Welcome to Visual Algebra Lecture 3.10, Centralizers. We've seen how the size of the conjugacy class of a subgroup is equal to the index of its normalizer. This measures how close or far a subgroup is to being normal. In this lecture, we will see an analog of this result for conjugacy classes of elements. Specifically, the size of a conjugacy class of an element is equal to the index of a subgroup called its centralizer. This is the set of elements in the group that commute with it. In this lecture, we will compare and contrast these two results, which are both special cases of the celebrated orbit stabilizer theorem about group actions that we will encounter in Chapter 5. Okay, let's get started. Recall back in Lecture 3.5 that we proved the following theorem. For any subgroup H of G, the size of its conjugacy class is the index of its normalizer. And the way to remember this is the size of the conjugacy class is the number of conjugate subgroups of H, and the index of its normalizer is the number of cosets of the normalizer. So the proof of this is to exhibit a bijection between these two sets, and here's what that looks like. So clearly, if we take anything in the normalizer and we conjugate H by it, we get back H. That's just the definition of the normalizer. But what this says is that if we take an element not in the normalizer and we conjugate it, we get back something else. And then if we take anything else in that same coset, like let's do A1 and we conjugate it, A1H, A1 inverse, then we get the same thing. And the proof of this is just to exhibit a bijection from these things down to here. I mean, explicitly, we define phi that takes a coset and sends it to AH, A inverse, and we show that this map is well-defined, one-to-one, and onto. In this lecture, we will see an analog of this for conjugacy classes of elements. Here's a key definition that we will need. The centralizer of a subset H of a group G, not necessarily a subgroup, is the set of elements that commute with everything in H. So here it is in set notation, the set of all x in G, such that xh equals hx for all little h in big H. And I'll let you check as an exercise that this is indeed a subgroup of G, even if H is not a subgroup. There's typically two cases that we'll consider. Even though we can define this for any arbitrary subset, we'll usually either assume that H is a single element, say little h, in which case we'll just write CG of H instead of CG of the subset containing H, or we'll consider the case where H is a subgroup. But in this lecture, we'll mostly just do the one where H is a single element. So here's two basic exercises. First of all, the centralizer of an element H contains at least the cyclic subgroup that it generates. Do you see why that is? The cyclic subgroup that it generates is just the set of all powers of I, where I is an integer, so this could be a finite or infinite set, but definitely h times h to the I. So h commutes with other powers of h. So this is hi plus 1 equals hi times h. The next exercise is that if x is in the centralizer, then every element in the coset containing x, that is of the subgroup generated by H, is also in the centralizer. So let's think why that is. So this is just the set of all x times h to the I, where I is an integer. So if x is in the centralizer, then this entire coset is in the centralizer because h times x h to the I is x times h to the I, which is, you see how this goes, right? X times h to the I plus 1 And then you can write this as x h to the I times h. And that's it. So individually, these are not all that impressive, but together what this means is that if you have a group G and you have an element H, and you take the subgroup that it generates, and then you want to find the centralizer, all you need to do is just check one element in each of the cosets. So every coset is either going to be entirely contained in the centralizer or not. In other words, the centralizer is a union of cosets of the cyclic subgroup generated by H. Throughout this lecture, I will continue with my coloring scheme that I used for normalizers and cosets. So if the centralizer of an element H consists of a couple of cosets, I will color those cosets blue. And the cosets that are not in the centralizer, I will color those red. So I guess it's a little bit different. It's because my red-blue is not exactly whether or not left cosets or right cosets, but they're with respect to this new definition of the centralizer. When we learned about normalizers, I introduced a definition that is unique to this video series in my book called the degree of normality. And you should just think of this as the proportion of cosets that are blue. So what is that? That's the total number of cosets divided by the number of cosets in the normalizer. And that is just 1 over the index of the normalizer in the group. What we're going to do here is define an analogous quantity for centralizers. And we'll call this the degree of centrality. Here's a formal definition. Let H be an element in G, and suppose that H generates a cyclic subgroup of index n. The degree of centrality of H is the size of the centralizer of H divided by the size of the entire group, which by Lagrange's theorem is just 1 divided by the index of the centralizer in G. Equivalently, this is just the number of elements in the group that commute with H divided by the total number of elements in the group. So think of this as the proportion of elements that are in blue cosets. As we did with the degree of normality, let's consider the 2 extreme cases and one in the middle. So if the degree of centrality is equal to 1, then H is truly central, because that means that the size of the centralizer is equal to the size of G. On the other hand, if the degree of centrality is 1 over n, so this is the worst possible case where obviously the subgroup generated by H commutes with H, that we showed that up here, but suppose no other coset does as well. In this case, we say that H is fully uncentral. It commutes only with the things that it has to commute with, other powers of itself. And finally, if the degree of centrality is strictly between 1 over n and 1, we'll say that H is moderately uncentral. The big idea here is that the degree of centrality measures how close to being central an element is. Let's do an example. This is the dicyclic group Dic₆ of order 12, and I've picked 3 elements to illustrate the various degrees of centrality. First, we have S that has order 4. Let's put the order up here. So it generates a cyclic subgroup of order 4. Next up, we have R squared, which has order 3. So it generates a cyclic subgroup of order 3. And R cubed has order 2. So it generates a cyclic subgroup of order 2 right here. Now let's look at the cosets, the left cosets of these cyclic subgroups. First up, we have the subgroup generated by r cubed. It has index 6, and r cubed commutes with everything, so all of these cosets are blue. All of these cosets contain 2 elements in the centralizer because the centralizer is the entire group. It has index 1. Now here's what I want you to notice. The index of the centralizer is also the size of the conjugacy class over here. So that 1 is equal to that 1. So in this case, r cubed is truly central. Next up, r squared. This generates a subgroup of order 3. Here are its 4 left cosets. And what commutes with r squared? Well, all powers of r do, but that's it. Nothing, s does not commute with it. So none of these things do either. So the centralizer has order 6 or index 2. We say that r cubed is moderately uncentral because this is another coset that commutes, or whose elements commute with r squared beyond just the cyclic subgroup that it generates. Notice that the index of the centralizer, in this case, is equal to the size of the conjugacy class containing R2. This is a preview for the theorem that's coming up next. And finally, we get to S. That generates an order 4 subgroup. I could call this S squared, S cubed if I wanted to, but I'll just use the same elements. And there are 3 cosets. And only elements in this cyclic subgroup commute with S. S doesn't commute with any of these other 8 elements. So the centralizer has index 3. So we say that S is fully uncentral. And not surprising, up here, if you look at the conjugacy class that contains S, it has size 3. So that's a preview as to where we are going. This is a slide that I introduced and went over in detail in lecture 3.5. So I will summarize it, but in less detail here. I encourage you to watch that video if you have not already. So what we have here is the group A4 and 3 different Cayley graphs highlighting cosets of different subgroups. N is normal. All left cosets are right cosets. So that means that the normalizer is the entire group. So the index of the normalizer is 1. N is truly normal. Over here, we have a subgroup K that has 6 left cosets. 2 of them are right cosets. So the normalizer has index 3. We say that K is moderately unnormal because more than just the bare minimum coset, left coset is also a right coset. There's one additional one as well. And finally, H has 4 cosets, and H is the only left coset that is also a right coset. So the normalizer is equal to H, and it has index 4. So we say that H is fully unnormal. So compare this concept to what we just saw with centrality. This picture should also look similar, both from earlier in this lecture and in lecture 3.5. Here is the theorem that I've hinted at, which says for any element H in G, the size of its conjugacy class is the index of its centralizer. So remember, the size of the conjugacy class is the number of conjugate elements, and the index of the centralizer is the number of cosets of C, G, H. So as before, we need a bijection between these 2 sets. We can go either way. I think it's a little bit more natural to go from cosets to conjugate elements. So let's start with this one. The centralizer of H is literally all elements that commute with H. So here we have powers of H. We also might have other elements in here that are, maybe we have an X here, maybe we have a little g here, but all of these elements commute with h. So this first box, these are the powers of h. So if you conjugate h by any of these because they commute, you just get h. Over here, these things do not commute with h, but I claim that if we take any two things in this coset, so we have a here, maybe an a1 here, that we will get the same element. So in other words, a1h, a1 inverse equals ah, a inverse. And same thing with here. In lecture 3.5 and in my book, I prove the normalizer version of this theorem, but I'm not going to prove the centralizer version because it truly is analogous. I want to leave that as an exercise in my book for my listeners and also for my students in my class. But I will give an overview as to how this is done. So we need to define a map from the cosets of the centralizer to the conjugates of h. And how do you think we need to define that map? Well, let's send a coset. I'm just going to call that xc instead of cg of x to the conjugate x, h, x inverse. And we have to first show that this map is well defined. Remember, what that means is if we have xc equals yc, then x, h, x inverse equals y, h, y inverse. So we have to show that. Then we have to show that this map is 1 to 1. Remember, that's like the dual of this. That's if these two things are equal, then the original cosets had to be the same. And we finally have to show that this thing is onto. And that one is automatic because if you have any x, h, x inverse here, you know exactly where that came from, the coset x, c. So I'll let you carry out the details for that. It's good practice. Here's a restatement of the theorem from the previous slide, but I want to speak of proportions of cosets, which are fractions. So I want to assume that h generates a cyclic subgroup of finite index in G. So the size of the conjugacy class of h is the number of cosets of the centralizer, which is just the total number of elements in the group divided by the number of elements that commute with h, which is 1 over the degree of centrality of h. Here's a picture. So what we have here is the cyclic subgroup generated by h that has index n. Now the individual elements are not subgroups, so I'm just going to put them next to the subgroup lattice. In this case, let's suppose that the conjugacy class of h has size 1. In other words, h is conjugate only to itself. That means that h is truly central. So the centralizer is going to be equal to G. It has index 1. Next up, suppose that the centralizer of H contains more elements than just the cyclic subgroup it generates, but not the entire group. So H is not in the center. So suppose the centralizer has index M, which is strictly less than N. In this case, the conjugacy class containing H is going to have size M. We say that H is moderately uncentral. It's got a class bigger than 1, but less than N. Finally, the third case is when the centralizer of H commutes with only the powers of H, only the things that it has to. So it has index N, and H is conjugate to N different elements. This is when H is fully uncentral. So the conjugacy class is as large as possible. Now, if you watch my lecture 3.5, you've seen a picture a lot like this, but for normalizers. And let me remind you of that right now. Here is the analogous theorem where I basically replaced little h with big H and big C with n, that is centralizer with normalizer. So remember, if n is normal, that means the normalizer has index 1 and it's conjugate only to itself. The conjugacy class has size 1. If it's moderately unnormal, means the normalizer is bigger than the subgroup itself, okay, but it's not equal to G. So it has index m, which is strictly less than n. And here is the size m conjugacy class. Finally, if the normalizer is equal to h, the normalizer has index n. This is the worst possible scenario in the sense that the conjugacy class is as large as possible. We say that h is fully unnormal. In summary, in lecture 3.5, we showed that the conjugacy class of a subgroup H contains the same number of subgroups as there are cosets of the normalizer. And the proof of this is by constructing a bijection between the left cosets of the normalizer and conjugate subgroups. In other words, two subgroups are conjugate by x and y if and only if x and y are in the same left coset of the normalizer. So we'd had to find a map from left cosets of the normalizer to conjugates of h in the only way that we could. We just sent a coset xn to xh x inverse. And we had to show that this was well defined, 1-to-1, and onto. Analogously, in this lecture, we learned that the size of the conjugacy class of an element is the index of the centralizer. And for that proof, which we outlined but are leaving as an exercise, we have to construct a bijection between left cosets of the centralizer and elements in the conjugacy class. In other words, xh x inverse equals yh y inverse if and only if x and y are in the same left coset of the centralizer. It's almost the same. Again, we have to define a map from left cosets of the centralizer to conjugates of h, and we do that in the only way that we know how. The left coset xc, I'll call this c for short, gets sent to xh x inverse. We have to show that this is well defined, 1-to-1, and onto. Finally, let's finish this lecture with a summary of conjugacy classes and related objects of subgroups versus elements. First of all, the objects. In the first cases, we're conjugating subgroups of G, and in the second cases, we're conjugating elements. The conjugacy classes are denoted the same in both cases, CL sub G of either big H or little h. But in the first case, they partition the subgroups of G, and in the second case, they partition the actual elements of G. Both of them have a related subgroup. For subgroups, this is the normalizer of H, and for elements, this is the centralizer. The size of the conjugacy class of a subgroup is the index of the normalizer, and for an element, it is the index of the centralizer. The so-called best case scenario, which is when the conjugacy class has size 1. For subgroups, this occurs when the normalizer is equal to G, which means that H is truly normal in G. For elements, this happens when little h is, the centralizer is equal to G, and this happens if and only if H is truly central. On the other end of the spectrum, the so-called worst case scenario, where the conjugacy classes have maximal size. For subgroups, this happens when H, the normalizer, is equal to H. We say H is fully unnormal. And for elements, this happens when the centralizer of H is equal to the subgroup generated by H. We say H is fully uncentral. In other words, the normalizer has to contain the subgroup itself at a base minimum, and the centralizer has to contain the cyclic subgroup generated by H, in other words, all powers of H at a bare minimum. Both of these are special cases of the celebrated orbit stabilizer theorem from chapter 5, which is on group actions. So there'll be a lot of neat stuff there, a lot of pictures. Some of the pictures from this lecture, you'll see analogous versions there. But in the meantime, we need to talk about maps between groups, homomorphisms, isomorphisms, the isomorphism theorems, and more. So there's a lot of really fun stuff here. There's some really cool visuals that I think you'll really enjoy, and it'll be new to most people, even to the seasoned experts. So make sure that you stick around for that. I'll see you then.